we are going to talk about the analog comparator. It is much simpler to use compared to the ADC in the previous chapter. In fact, it is so simple that this chapter is quite short. This is the outline of this chapter. First, we have a tiny little look into the past and see that we already met the analog comparator earlier in the course. Then we are going to talk about how to configure it and what those configurations do. The analog comparator already crossed our paths in the course earlier. We always dismissed it though, and I promised to talk about it later in the course. For instance, the comparator was already shown in the block diagram of the input capture unit when we learned about timers and counters. So here we are and talk about it. And even in the last chapter, we already saw a comparator, albeit a different one, and that was integrated into the ADC. Its task was to compare the analog voltage generated by this digital to analog converter or DAC against the input voltage from one of the channels. The ATmega has a dedicated analog comparator which is quite easy to configure and which allows a simple comparison of analog voltage without the need to sample and convert the data. The analog comparator is primarily connected to ACIN0 and ACIN1. In addition, it can also be configured to use neither of them. For instance, it can be connected to the ADC pins here in yellow. What else it can be connected to instead, and what the consequences are, we will see in a minute. And here's the block diagram of the analog comparator in all its beauty. Right here in the middle is the actual comparator. On the left side are the pins ACIN0 and ACIN1. Let's see how we can use it in the ATmega. The ACSR is the configuration and status register for the comparator. First, as usual, we have the main switch ACD, which is here in the block diagram. Please keep in mind that ACD stands for Analog Comparator Disable. Therefore, writing a 1 to this bit turns the comparator off. By default, and after a reset, the analog comparator is active. That is in contrast to, for instance, the ADC, which needs to be turned on explicitly before it can be used. It will maybe save a few hours worth of debugging time in which a developer keeps wondering why the comparator always returns the wrong result consistently. If not needed, the analog comparator can be turned off so it does not contribute to the overall power consumption of the ATmega. There is no harm in turning it on again, and only if you need to take a measurement. The next bit in the status and control register is ACBG, which is located here. Apart from connecting ACIN0 to the positive input of the comparator, we can also attach the band gap reference, a quite stable voltage to compare against, to the comparator. We had the same band gap reference also in the last chapter about the ADC. It is the very same reference. Hence, if ACBG is set, the band gap reference is connected, ACIN0 otherwise. The next bit in the ACSR is ACO. The analog comparator output is 1 if the positive input is higher than the negative input. For instance, if a 1.8 volt source is connected here and a 1 volt source on this wire, then ACO will be 1. Okay, what else do we have? Next bits are ACI and ACIE. They are responsible for generating an interrupt. As you can see, ACIE is ANDed with ACI. That means that ACIE is the interrupt enable, while ACI is then causing the interrupt request. If ACI is activated, depends on 2 more bits, ACIS1 and ACIS0. Depending on the setting of ACIS1 and 0, ACI is only active in specific situations. If, for instance, both bits are cleared, any toggle of ACO causes a change in ACI. However, we have the option to set ACI only if, for instance, the comparator toggles from 0 to 1 or vice versa. So we do not have to check these conditions in software by comparing ACO against its old state and check if it changed when we poll it again. And the last bit that we skipped earlier is ACIC. As you can see here, ACIC goes straight to the timer 1 capture trigger multiplexer. What does it do there? ACIC comes in here and controls this multiplexer. It allows to forward a signal either from the ICP-N pin or from the analog comparator. If that signal arrived, it causes the value of TC and T1 to be copied into the ICR, the data register of the input capture unit. Hence, we get a timestamp of the event when the voltage crossed the threshold and the comparator output toggled. And the interrupt request ICFN will let us know that such an event occurred. There is only one configuration setting left that we have not discussed yet here in this corner. We have the ADEN and ACME bit. The ADEN is the main power switch for the ADC in the ATmega. And even ACME was part of the ADC control and status register. What does it say here? Well, if the ADC is off, then ADEN is 0. Since ADEN is negated at the AND gate, this wire will be high if ACME is set to 1. This causes this switch to connect the negative input of the comparator to the ADC multiplexer output, while at the same time it disconnects AIN1. That means that all the input channels of the ADC, that is ADC0 to ADC7, the band gap reference, ground, and the output of the temperature sensor, are forwarded to the comparator instead. However, that only works if the ADC is off. And what channel is forwarded? That is set in the ADMUX register that we had in the ADC chapter. The setting introduced there regarding the MUX 3 to MUX 0 also applies here. Like in the ADC, in which the digital read part of the pins can be deactivated to reduce noise and power consumption, we have another DIDR that can do the same for the AIN pins. Briefly, the problem is that especially in the region between logic 0 and logic 1, the flip-flops of the digital read section of the pin could start toggling at a very high frequency because the digital state of the flip-flops in this region is undetermined. To prevent the excessive power drain due to the constant status updates of those flip-flops, they can be turned off using DIDR1. And that is already all about the analog comparator. We learned that it is able to compare analog voltages, and it is helpful if only the information that a voltage is higher or lower than another voltage is required, without the need to know what those voltages actually are. Instead of converting them into the digital domain and comparing them in software, we just do it in the analog way, which is a lot more efficient. If the ADC is not used, we can even use its analog inputs. Hence, with AIN0 and 1, we have 8 external channels available, or 10 channels if we consider alternative packagings, which have the channels ADC0 to ADC7 available instead of ADC0 to ADC5 only. Well, you might ask, what is the purpose of the comparator after all? It can do much less than an ADC. That is true, but many times engineering is about simplicity. Imagine an example. You would like to know if the air temperature is 25 degrees Celsius or higher. Using the ADC, you first have to calibrate the internal temperature sensor. Then you have to keep sampling it from time to time to check the temperature. Using the analog comparator instead, the calibration can be done by applying the required voltage to AIN0 and adjusting it till the comparator output changes at 25 degrees. In addition, instead of sampling the data in time intervals, which is similar to polling a register, my program can do something else, or even sleep and save power, since it is getting informed when the temperature crosses 25 degrees. No need to sample anything, since I'm not interested in any value or information other than when the threshold is crossed. Another example, there is an exercise at the end of the chapter. In this exercise, you will have to build a proximity sensor circuit. It uses infrared LEDs and receivers to know if objects are too close. Those kind of sensors are often used in robotics, such as smart vacuum cleaners to detect stairs. So what is next? In the next chapter, we will talk about the memories that we have in the ATmega, which allows us to store configuration data such as the offset and gain factor for the temperature sensor calibration that we discussed in the chapter about the ADC. But first, have fun in the exercises. After that, I'll see you in the next chapter. Thanks for watching.